Okay, a really quick look at some techniques I used creating this concept model of maybe a key fob or some kind of navigation device or whatever it was. It doesn't really have to be nailed down to any one particular thing. Anyway, so I will roll this back. There's not that many features, like less than 50 features for this whole thing, but I'll show you some of the approach behind it. Now, I started out, and you'll notice there's a lot of things in folders here. I tend to use folders and named things quite extensively for organizing my part studios like this. So I've started out with two curves, and both of these curves are splines of one form or another. And in fact, these are degree 3 B-splines, actually Bezier splines are used in the sketcher. I can edit that. You'll see that I've defined a couple of, I've fully defined this one actually. These are equal length. There's a symmetry around the middle here. There's a certain amount of dishing to it like that. So with these two B-splines, Bezier curves, I'm going to create a boundary surface. And the boundary surface just uses those two edges as definition. I don't need to have pair for this particular case. I just use one U curve and one V curve as it turns out. Now, if I have a look at the curvature analysis of this, if I first look at the control points, as expected, there's 3 segments or degree 3 in each direction. 4 control points is degree 3 with a single span curve like this. And that pretty much guarantees that this is as high a quality surface as that I'm going to be able to get. You can look at these individually or in the both directions of U and V. We've got a very, very nice curvature here. So the point is that when you have a main surface, maybe something else you're going to refer to, something else that will be trimmed later, but essentially forming the A surface or the styled main surface, block surface, there's lots of different names for this. You would use as fewer control points as possible, and I think 3 by 3 or degree 3 in both these directions is perfect. Right? This is the shape we want without going overboard. The next thing I did was to create a trimming cut for it. So just on this top plane here, I created another curve in the sketcher, and if we have a look at this, I've actually used a technique here again with a Bezier curve. So it's going to have nice symmetry across here. It's going to be curvature continuous across here, but have some nice shape there. All right, so there's my sketch. I'm now going to extrude this to create a shape like this. And then I'm going to perhaps split and get rid of the tool that we used, leaving just that nice dished face. Now this face here, which has got the profile that I want for my device, if I look at the curvature analysis again, or the surface analysis here, you'll see that this is using still the original degree 3 by degree 3 B-spline surface. It's just been trimmed. So we haven't used these trimmed edges to actually define the boundary of the surface. It's just a trim of that original surface. In other words, the curvature of this surface here is as good as it was before the trimming. And this is a really kind of an important main mantra to stand by, is that don't mess with the surface, don't redefine the surface if you don't have to. Always use the highest quality form of it that you possibly can. From here it was a mirror. I mirrored this across the top plane to have the back and the front. And I have this one called a main surface down here. All right. Next, it was a matter of creating the side profiles. So again, I used some sketches that were Bezier curves. And if I look at the control points, it's a 1, 2, 3 degree 3 curve here and here. If you haven't noticed by now, I really like to use the diagnostics extensively all the time, and I recommend you do so as well, because the sooner you can catch problems and go and fix them, the better. Rather than waiting 200 or 300 features and then having to go back to feature 10. All right, so we've got a nice set of curves here, and we've got these edges that we're going to use. Firstly, I'm going to create a couple of surfaces I call helpers, and I'm going to use those helper surfaces here to help me define tangency when I create this corner. And to create the corner, I'm going to use a boundary surface like this. The boundary surface was between those two sketches, as you imagine, and the top and the bottom, which was from the original split. We have a look at the isocurves. We have a nice clean surface around there, and these helper surfaces aren't merged in. I'm actually just going to hide them, and I'm going to do a couple of mirrors. I'm going to mirror this once there and then across again, and then Boolean them together to create a single surface that just is what I've called main surface. So you can delay on that Boolean until you've done this mirroring, or you can actually use the mirror. There's an add option in the mirror if you wanted to, rather than use the separate Boolean, but up to you. From here, it's a matter of starting to add some kind of aesthetic features to this edge that's a little bit sharp at the moment. For this, I actually happened to use a face blend. The face blend here is an asymmetric face blend with curvature continuity. It's a bit of a mouthful, but let's have a look. So I've chosen the original surface there. If I just hide that a bit, that was the first surface, and the other one was this side face around here. There we go. So the first one was then there, second one was there. I've got tangent propagation turned on, so the surface will, the blend, the face blend will flow around wherever it can continue tangent. You can turn that off, and you can have a lot of controls over face blend. You can choose only adjacent surfaces, even if they're not tangent, or you can add your own degree, sort of amount of flow. So 0 degree, that's tangent, but we could put it up to 10 degree, and it would include everything that is within that tolerance. In this case, let's use tangent. I'm going to use a simple rolling ball fillet, although I don't have to. I could use a swept profile or a spine-based fillet, and that's blend, which is probably in another demonstration. All right, so rolling ball blend, and I'm going to use a width fillet. I'll just turn the preview back on. It's going to be a width fillet, which I'm controlling the distance across the chord here, or the width, 3 millimeters. I've made it asymmetric, so I'm going to change the ratio from one measurement to the other. You can see here if I if I put it to 0.5, it's going to be a much more even fillet, but 0.9 is where I wanted it to be. And what else here? It's a curvature continuous. Interestingly, with a face blend, you can actually get it to do chamfer operations as well. A face blend is an extremely powerful set of tools. So you can choose a circular, or that's a circular that would just be tangent, or G1 at that boundary. In this case, I wanted a curvature fillet. So it's going to be G2 at these boundaries for the blend. There's a lot more controls about the constraints and the limits and how we can trim these blends. Again, that's going to be the subject of a different demonstration. Suffice to say that we have the same thing kind of going on the top. Right, so having this done, this is just the general outer shape. It's nice, we could have a look at a few things like normal. We'd use zebra stripes. Look at the nice continuity between the face blend and the top there. What else have we got there? I mean, again, these top surfaces we had before are still these very nice 3 by 3, degree 3 by degree 3, and you can still see that even with the the face blend that connected in from the side faces to the top. It doesn't change the top face at all. So that's very nice. And again, these tools that we want to use for visualization of the curvature, it's important to use them early and often. things like if we have a look at this face here, look at the nice control points. It's fairly well spread out. There's a bit of a cluster of control points here as it tries to, and ensures that there's curvature continuity into the next face. We can have a look at that there. Just look at the V curves, the blue ones there. And if we look at this one here, you can see where the thick bit ends, which is the top of the comb. If we extend that across the face, that meets exactly with the combs that are coming from the face itself, just to give you the reassurance that that's a G2 connection there. Of course, G3, the acceleration between here is matched as well. Now, this is not a G3 connection in this case, this is just a G2 connection, as defined by what we asked it to do back here in the face blend. All right, so analysis aside, now we can turn a few of those sketches off with a Shift P and have a look at the next bit. Now, I won't go through this in great detail because it's fairly routine, but I just created a little recess here. I created a section, split it down, offset it a little bit, and to give it the depth here, and then created some connections using boundary surfaces again for these 4 sections here. And then I went on to create some buttons. Now this was, if I hide the main surface and show you the sketch for the button, there we go. First thing I did is just create a variable. Sometimes it's handy to be able to go over to the variable panel here and be able to just play with that. Now we'll do that in a second, but the sketch here, now I'm using some straight sides, and then I've got this segment here which is actually a Bezier curve as well, and it's got 8 control points. Oops, you can see those control points: 1, 2, 3, 4 and 5, 6, 7, 8. Now if you align the control points up as I have here, and I've just made them these segments here, these parts of the definition of the Bezier curve, equals distance, equal lengths there. So 1, 2, 3 equal lengths, and 1, 2, 3 equal lengths, and then I've given a couple of dimensions which happen to be equal as well, to give a nice squared corner. But if you have a look at the curvature on this, you see that the curvature comes down, and it just starts to even out like an aeroplane landing. So it's a smooth landing into the curvature, which is 0 over here. And this kind of a smooth landing is kind of a typical of a G3 connection. So this curve here is G3 to that one over there. I've done that using mirror on all 4 corners, and that gives me a nice button. In fact, I can show you what the facet, this little length here, which I called the facet, is actually being driven by the variable. So it's the same all around. And if I go to the variable itself and start playing with it, like maybe 0.5 or 0.2, 0.3 was kind of the just right position. That was a little bit too square. That one looks a little funky. I think 0.35 or 0.3 or something like that was the right value. All right, then I extruded this. All right, and there's a couple of, I extruded this so that I could intersect it and do some button work. Now the interesting thing is that I compared using a ruled surface using an extrude surface, and a little bit like the earlier presentation I made where the difference between a loft and a boundary surface, the kind of where the control points are, and effectively the curve approximations that go on, to be exact, at the boundaries. The same thing happens when you use an extrude versus a ruled surface. Now, I won't go into it now, but in this case the extrude is the one that keeps the definition of the sketch, the Bezier curves there. So if we looked at the control points and the control point grid there, and then compare that to the edge of the surface itself that we created from it, they're going to be exactly the same. No reapproximation was needed. Right, so then I finished that off, created a couple of buttons, and I actually have two buttons. There we go, 1 and 2. Now this is the end of the concept, or the skeleton master model, whatever you want to call it. So this is where I would stop doing things in the Part Studio. Now there's a few more features in here. I was just experimenting with creating something maybe like a hook or something on the bottom there, but not important for now. This is really just providing me the reference surfaces that I would use for downstream purposes. And the way that I did that now is I would create a new Part Studio, and the first thing I'll do is derive in, using a derive feature, from that concept skeleton. So we go and we open up what's in the Part Studio called Fob Skeleton, and we find our main surface. We can bring that in, and we can also bring other sketches and planes and other things that might be, just for fun. I can bring in the end and the side just for reference purposes. So that is a derived feature now, and that's the only thing that's in the feature tree at the moment. I can see the sketches there. I can turn them off, leaving the main surface. And it takes on the same name from before. In fact, with this way of doing it, this is associatively linked to the original main skeleton concept surface here, the one that we created called main surface. So any changes I make here will be reflected over here in this Part Studio fully associatively. Now, there is a slightly different way you can do this, which is to take this detailed, or where we're going to do some detailed design or some downstream design, we can actually take this into its own document. And if we take it to its own document, because documents are where the version control is kept, we could have this detailed derive refer to a particular version in the original document here. So for now, when we're just trying to rapidly do things and expecting a lot of changes back and forward, it's probably good to keep this in the same document, and so that we have the associativity automatically updating. And later on, when we want to maybe nail things down in a more detailed fashion, we could pretend or potentially split this out into its own document. But for now, this is how I would start things, and then I might look at splitting things, creating a shell from this, removing sorts of faces, putting in plastic molded part design features like lips and maybe some screw bosses. I've done some of that already. Over here, I'll take you to this detailed one, which is where I did some of those same things. I split this into two parts. I created a pretty simple, lip and ear type of approach in there. Removed some space for the screen, put in some fillets. In this case, it was a pretty simple edge fillet, I think. Edge fillet with curvature control on that as well. So a nice smooth bezel around there. And now that I've got those two parts, I can finish detailing and put in the screw bosses and potentially use this in an assembly. Actually, let me look at this as a section through here. You can see where one part is meeting the other there. So because they've been derived from the same concept part, I know that they're going to fit exactly, and I would put then an allowance, kind of an assembly tolerance or a manufacturing tolerance that will allow it still to be assembled without jamming. There we go. There, and of course we would probably do an exploded view just to see things going. Right, just at this point, I would probably take this over to a render studio and do a rendering as such, and then look at reflections in even Another way, we've gone through all sorts of different techniques, whether they're curvature combs, zebra stripes, all sorts of ways of doing it. And don't forget that rendering, and a photorealistic rendering like this using Render Studio, is a very, very good way to evaluate reflections almost in a bit of more of a real world situation, other than zebra stripes, Gaussian curvature, and those sorts of other tools. So with that, I'll finish up for now and think about some other things to show.